In this lab, we're going to look at Boyle's law. We're basically going to take a sample of air inside a gas syringe, and we're going to compress it by adding on reams of paper. By observing the relationship between the pressure exerted by the reams of paper on the volume of the column of air inside the syringe, we can see the relationship that exists in Boyle's law. The setup for this lab is pretty straightforward. We have a gas syringe here that can hold up to 30 milliliters of air. We have a rubber cap for the syringe that can trap the air inside the syringe. Okay, and we have this set of two wooden blocks. Basically, the syringe can fit inside, the tip of one goes into one block, whereas the cover goes into the other block, kind of sits in like this, and we have our setup that basically looks like this. There we go. That's a little bit easier for you guys to see it. Okay, so basically we're going to put our reams of paper on top here, and as they push down on our syringe, we're going to see how that volume reading changes. All right, and that's basically how this lab's going to run. It's a pretty straightforward setup. But in order to calculate the pressure on this column of air, we first need to figure out the cross-section area of the column of air inside our syringe. So to do that, I'm going to remove the plunger. Okay. And we are going to use a ruler to measure out the diameter of that bore. I took a video of me measuring the diameter of this syringe, but as you can see, the bore has a little bit of a plastic lip on the inside, and you need to measure from the inside of that lip. And so it's kind of hard to get a ruler over there and measure it, at the diameter and get a really good, accurate reading that way. So what I thought might be an easier, more accurate measurement, and easier for you guys to read by looking at a video, is I took out the plunger from the syringe, and I'm going to hold a ruler to the central point, that tip on the plunger. All right, I can't hold the ruler too close up here or all the way down here, because that perspective distance tends to mess up the reading. So what I'm going to do is I'm going to keep this block of wood here and hold that steady. Okay, and I'm going to try and, so keep the plunger against the block of wood, keep the ruler against the block of wood, and try and line up the ruler to the tip of the syringe. All right, I think everything's lined up. You should be able to make your reading based on this video. All right, we're now ready to start taking our actual volume measurements. So we start off by putting the plunger back into the syringe, okay? And we want to wind up with about 30 milliliters. So I'm going to use that line over there, this line, the line that's, I guess I should hold it up with this. So the top line there to mark my volume reading. So I'm going to push that up, put that into our syringe, and there we go. You can see now that top line is touching the 30 milliliter mark. Hopefully that's a little clear, not too blurry. But yeah, that's my 30. I've got 30 milliliters of air inside my syringe now. I'm going to add this rubber cap here, okay, and that should trap that air inside there. Now we'll keep that over here and add our second block of wood to that. We're going to add our reams of paper to this block over here, and then try and make our volume readings. Okay, but in the meantime, though, we first need to get a volume reading of just this setup as it is, because that is the volume reading of, well, 0 reams of paper, but also of the surrounding air pressure pushing on this block of wood. I rotated the syringe to make it a little bit easier to view. So there is a little close-up of that that volume reading on our syringe. So note that it's actually going to be a little bit lower than 30 milliliters based on the, if we're using that bottom, well, the syringe is upside down now, so the bottom line over there, make a note of what that's closer to. Okay, I'd say since the individual volume markings there are to the nearest milliliter, obviously it's slightly off, but based on the precision of this syringe, you would probably mark that as 29 milliliters as your initial volume. Okay, so please note that this is the volume without any paper on our syringe. And let's go ahead and add some reams of paper. Okay, so we're going to go ahead and add on a ream of paper. So, we've got just these identical reams of paper here, so I'll add this first one here. This gets a little wobbly, so I'll try my best to try and keep it steady. Ideally, you would do this with a lab partner, and one of them would hold this relatively steady and avoid toppling over, while the other person would stay at eye level and try and make a reading. So I'm going to try and hold this steady and take a picture and hopefully not let this whole thing collapse while I'm at it. Okay. Alright, I'm going to add a second ream of paper to this. This is going to get a little tougher to balance. So hopefully it'll hold steady as I try to take pictures. Just try and hold that steady. I've got to be careful not to actually push on the top of my stack of papers or try and hold it up or anything like that, because that could affect my force readings, my pressure readings. Let's try working on this and try to get this to center a little bit. There we go. Oh, that actually worked pretty well. Let's add a third one. This is the worst game of Jenga ever. Alrighty, I'm going to add a third one. I'll probably going to cut down the narration here and just keep on adding reams of paper and take pictures while I'm doing it, just because I think this is going to be kind of hard to balance at this point onward. So here's 3. Just going to hold that steady. Here's a picture. And here's a 4th ream. And there's a picture of the reading. Here's our 5th and final ream. Okay. I'm trying to take care not to push down. I'm just try and hold this steady, and just stop it from wobbling too much or tipping over. And there goes a picture for that. Okay. And that's our 5 pieces of data. Well, 6 if you count it without any reams of paper. Woofda. Alright, so now that we've collected our data, we're going to walk through the actual lab report for you. And what I want to do here is to use this lab as an opportunity to learn some skills involving spreadsheets. Okay. When I was in high school, I took an information technology course, and it covered using Microsoft Excel. And when I got to college as a chemistry major, I was kind of amazed at how much the skills I learned in that IT course kind of helped me just manipulate numbers, to manipulate data and sort of treat numbers. It made graphing data a lot easier, analyzing data a lot easier. And basically it was, for one of those skills that you just randomly pick up in high school, I was really kind of blown away with how much it came back to help me, both as a scientist and as a teacher. And over the course of my teaching career, I'm kind of amazed at how few students actually do learn how to use a spreadsheet program. And so I like using this lab as an opportunity to sort of learn some of those skills, learn those techniques, because you never know. Some of these things you're going to learn in this lab might help you in other avenues, not just chemistry. All right. So basically, with the data we collected, we've collected volumes, and we can calculate the masses of paper that we added. All right. But essentially, we're going to fill out this table over here. Now, you could sit there and do all the individual calculations for this table, and it would be a very tedious task. And of course, you can do it, but I'm going to show you now how we can get a spreadsheet program to do the calculations for us and therefore save us a lot of work. Okay? All right. And we're also going to get this spreadsheet program to plot these graphs for us. So you'll notice that I have a graph for pressure versus volume, and another graph for pressure versus the inverse of volume. All right. You're going to need to produce these two graphs, and they're a great way of graphically understanding Boyle's law. Okay. Now, you could draw this graph, you could sketch this on here, and I typically leave that open to instructors. Some instructors prefer to, let their students have extra graphing practice, and this is not a bad place for that if you want to practice manually graphing. But I feel like we get a lot of practice in some of our previous labs, and so I want you guys to plot these graphs that we're going to draw in our spreadsheet program. Okay, and again, I'll show you how to in this video. Okay, the nice thing about using a program to do the graph for you is we're going to draw a graph of best fit. We're going to draw a power curve for the first graph, and the second graph will be a linear, like a line of best fit. Normally, you would draw that just kind of eyeballing it and taking your best, sort of your best attempt to draw the line evenly between all the points. The nice thing about using a program is that a computer is going to do this for you, and they're going to draw a graph that's like mathematically perfect, essentially. So again, this is just one of the nice things about using a spreadsheet program to do this work for you. And once again, I will walk you through that in this video. All right. The other thing we can see here is that it'll give us some extra information about our line. I'll show you how to get a standard deviation for your line of best fit. That basically just tells you how good a line of best fit it is and lets you know essentially how precise your data was. Okay. All right. So with that in mind, let's go ahead and start converting this graph, this table, into a spreadsheet. Now, when I used to teach this lab in person, I would demonstrate this on Microsoft Excel using one of the lab computers. The idea here, of course, is that even if you don't have Microsoft Excel at home, you have access to one of the school computers, and all of them have Microsoft Office Suite, and therefore would have Microsoft Excel as the spreadsheet program you could use. All right, and I just figured that was a very common spreadsheet program, and using that was a good way to kind of cover all of the basics in a way that everyone could follow along. Now, that being said, if we're, well, as of filming this, we're in the midst of a pandemic, and we're trying to limit the number of people going to campus. So if you're doing this at home and you don't have access to Microsoft Excel, what you can do instead is I'm going to show you how to use Google Sheets in this video. Google Sheets is, of course, the Google Suite spreadsheet program, and I'm essentially going to show you how to do all of the same things that you can do on Microsoft Excel. All right, there are a few small differences here and there. I think Excel probably is a little bit more robust, a little bit more powerful. You can do a few more things, and there are like little things that it does that that aren't really super important, but like it goes to more decimal places and things like that, or you can adjust the decimal places and so on. But for the bottom line is you can use your Google Sheets, which is something that you have access to just by having a school email address, since we use the Google Suite for our email and so on. Okay, so let's work on doing that. All right, so to get to Google Sheets, just open up a browser, type in sheets.google.com. Okay. You may be asked to log in to Google, so you could use your SUNY Adirondack login information and just log in here. So you can see here I've just logged in using my sunyacc.edu email address. Okay, there you go. Okay, I've used my SUNY Adirondack account there, and yeah. So then you want to select a blank worksheet. All right, and that's where we're going to start with. So we're going to basically enter in the same table that I showed you earlier, and we're going to use our sheet here to represent the rows and columns of that table. Okay, so basically we have columns here which are marked with letters, and we have rows that are marked with numbers. Now, each of the intersections of these are called cells. Okay, so each of these little boxes are cells, and you can refer to them by their row and or by their column and row using their letter and number that correspond to that. So for example, right now I'm in cell A1. Okay, so if I click on this one at random, this is cell D7. All right, I'm going to use that first row to put in the sort of headings of our different columns. So over here I've got my number of objects. I'll just say numbers of reams of paper. Okay, oops, I need to edit that. So if I click over here, that'll allow me to do that. Number of reams. Okay, I believe we have then a column for pressure, a column for volume, column for 1 over volume, a column for pressure times volume, and the pressure over volume. Okay, and so let's start entering these numbers. I've gone ahead and I'm going to copy and paste our volumes that we got from the video. So rather than actually watching the video and stopping it, or having you go back and do that, I mean, you're welcome to, but here are the numbers for you if you like. Okay, and again, it's probably not a bad idea for you to double check these numbers. These are the numbers as I saw them, but perhaps you saw them slightly differently, and I'm sure those numbers will still work out fine. For our reams of paper, remember we started off with no reams of paper, just the blank wooden block. So we're going to have a 0 there, and of course 1, 2. I could just type in 3, 4, and 5, but I'm going to show you a silly little trick here. If you highlight, basically numbers 1 and 2, and you move your cursor to this bottom right where it turns into a cross, you can click and drag this down and it'll automatically populate those numbers in for you. Kind of silly when we're only counting up to 5 here, but if you had a longer list, this would save you the hassle of having to type out sequential numbers. Anywho, random thing we've learned there now. So we're now going to fill out this column here. And we could do the calculations based on how the lab manual tells us. It kind of walks us through the process on the page before the table. But I'm going to use that information, and I'm going to get our spreadsheet to do the calculations for us. Okay, so just a quick rundown of how the lab manual explains what's going on with the pressure. We're taking our reams of paper, which are heavy, they have a mass, and that mass is exerting a force due to gravity on our column of air. All right? Now, our column of air has an area, right? It has a cross section, and you can calculate the area for this, which is why by the way, we took the length or the diameter of the bore of our syringe. Okay, so we're looking at the force divided by the area. That's what pressure is. Okay, that's how we're calculating pressure here. So we're taking the force from our reams of paper based on the weight of the reams of paper in grams, and we are going to divide that by the area of our column of air. Okay. Now, in addition to this, we've got to take into account air pressure, which your lab manual informs you is 1,034 grams per centimeter squared. So we're going to add that to each of our calculations. Now, again, you could sit here and plug all of that for each calculation. You could do that calculation manually for each individual cell. But that's a lot of work. Okay, there's 6 of these calculations we're doing, and rather than doing them 6 times, we can do this once and have the computer calculate the remaining 5 ones for us. Okay, so how are we going to do that? To tell the computer that, or to tell this program that we want it to do a calculation for us, we first type in an equal sign. Okay, so we're typing in instructions now, and the equal sign at the front of what we're entering into this cell tells the program that we're entering in a calculation and we want it to do the calculation for us. Okay, so we want to take into account the mass from our reams of paper. All right, so I'm going to put in a couple of parentheses here because we're going to wind up closing these parentheses and you'll see when I'm done typing. But let's start off with the fact that a ream of paper weighs 5 pounds, which when converted into grams is 2,268 grams. Okay, so we've got that mass from our from each ream of paper, but of course we want to multiply by the numbers of reams of paper. Okay, now you could do this manually. You could put 0 for this first line, you could put 2,268 for the next line, you could put 4,500 and whatever for the next line, and so on. But again, we want the computer to do the work, not us. So what I'm going to do is I'm going to take the mass of a ream of paper, 2,268, and I'm going to multiply it by my reams of paper, but instead of writing in the number of reams, I'm going to sort of select where that's written in my spreadsheet. Okay, so I'm going to put my multiplication sign, which, by the way, in a computer program here, a multiplication sign is an asterisk. Okay, so you put your asterisk. Okay, it should be right above your 8 key. So if you hit Shift and 8 on your keyboard, that'll put in the asterisk. Okay, now instead of writing in 0, because I'm doing this for this first row where there's no paper yet, I'm going to click on where the number of reams of paper is written for that row. And when I click there, it tells me the location of that cell, A2. Right, it's in column A, row 2. I could have even typed A2 if I wanted to, but I just wanted to show you, like, when you click on a cell, it'll automatically put that in there for you into the formula. Okay, so I'm going to close parentheses here because that's the mass from my paper. Now I need to divide by the area of my column of air. Now my division sign here is a slash. Okay, so just as a multiplication sign is an asterisk, for computer programs, a slash is the divided by symbol. Now, I need to calculate my area of my column of air. And again, your lab manual walks you through this. You should look at the video, determine the radius of that column of air, or you can find the diameter and divide it by half. Divided by 2. You can find half the diameter is the radius. For me, when I measured it out, I saw the diameter was about 2.2 centimeters, and therefore the radius was 1.1. So if I take pi r squared, so I take 1.1 squared, and multiply that by pi, which is 3.14, I essentially get a diameter of 3.8 centimeters squared. Okay, so now I'm going to close that second set of parentheses. So what I've got here, of course, is the pressure exerted by my reams of paper, however many I have, divided by, over that area of the column of air in my syringe. But of course, remember, this is not the only source of pressure in this experiment, okay? And the lab manual will remind you that you have to include the air pressure that's being exerted as well, right? So the surrounding air is also just pushing down on that block of wood and therefore the syringe. Okay, so we have to add, so I'm going to add a plus sign here, plus 1,034 grams per centimeter squared. That's the pressure that's from the surrounding air. Okay, now at this point, we've accounted for everything, and so if we hit enter, the computer does the calculation for us. Okay, now you're probably saying to yourself, okay, big deal, I could have calculated that easily enough, right? And you had no reams of paper, so really all I had was my 1,034, grams per square centimeters of pressure. Okay. However, here's the magical part. If I click on this, all right, if I move my cursor to that bottom right, you can notice it turns to that cross again. If I click and drag that down, the computer does all the calculations for me. Okay, I don't have to individually calculate all of the next 5 lines. By putting in that reference to A2, if you click on any of the cells, you can see how the computer automatically swaps that out for the other values. Okay. Now, by the way, if this looks a little bit disjointed, like you've got so many decimal places here and nothing here, and you want this column to look a little bit more uniform, your spreadsheet program, so in this case Sheets, but even if you're using Excel, we can use our program to make this look a little bit neater by changing the number of decimal places for the whole column. So, click and drag to highlight all of these values at once, and you can go to, let's say, 2 decimal places if that sounds like a good number for you. Okay, so you can see just like that, we filled out an entire column of our periodic table. And we can do the same thing for the other columns as well. And if anything, they're going to be a lot easier to fill out. So for example, this next column has 1 over volume. We want the inverse of the volume. But instead of sitting there and calculating for each line, like 1 divided by 29, 1 divided by 18, and so on, we can get the computer to do this for us. So again, to enter a formula, hit the equal sign, so that the program knows you want it to do a calculation for you. So we're going to take 1 and divide it by, so we use a slash. Okay, that's how a computer recognizes the division command. And now again, instead of writing out 29, we're going to put that reference to where that 29 is, because that reference is going to change for each line. So in this case, we could click on this, or I could just type in C2, because that's where that cell is located with that volume, and I hit enter, and the program does the calculation for me. But if I click on that cell, and I move my cursor to the bottom right where it becomes that cross, and I click and drag it all the way down, notice it has done all the calculations for me. Okay, and again, this looks a little bit messy because we've got different decimal places here, so we can use this button up here to change the number of decimal places. Let's say we want to go to, I don't know, 4 decimal places sounds reasonable. Let's do that. Okay, so you can do that for the rest of this table. So this column for pressure times volume, of course, I can let you figure that out. Hopefully you're not, you could do that by yourself, or you could simply just pause this video and watch me doing this. But this will give you an idea of roughly what your answer should be. Okay, and of course here, notice we have, actually, like you can see here with pressure times volume, notice how all these numbers are in that in that ballpark of about 29,000. I'm just going to point that out for no particular reason. Here's the pressure divided by the volume. Okay, so again, it's going to be pressure / volume, and there we go. So I have all of those calculated out, and we can move on. Okay, so now we have our table completely filled out, and I did this in probably a couple of minutes. So this takes you 2 minutes as opposed to what probably would take about 20. So you can see again that this is one of the key advantages of having of being able to use a spreadsheet program. It really cuts down your workload and your time taken to do some tedious calculations, especially like if it's the same calculation over and over again. Okay, now here's the other really useful thing. Okay, I pointed out in the lab manual, we want to graph this data to understand what's going on. So we want to get a graph of pressure versus volume, and we also want a graph of pressure versus the inverse of volume. So we're going to get this column on our x-axis for our second graph. So let's look at how to create graphs and insert them into our table. So the first thing I want to do is I want to select my y values, the things that are going to go on the vertical axis of my graph. So remember, we're plotting pressure versus volume here. So we want to highlight our pressures. Okay, so I'm just going to click and drag just the numbers for that pressure column. Don't include the heading, okay? Just the numbers. Now, we're going to click on Insert and Chart. Now, the default oftentimes is a column. In this case, I think it may have defaulted to scatter just because I've been doing so many scatter graphs. But in case it gives you a bar graph or a column graph, if you just click on this, it might give you suggestions, or if it's, like I said, if it's selected this one, you can scroll down to where it says scatter and just select scatter. Okay, but the bottom line is you want a scatter graph for what we're going to do here. Okay, so make sure you select that accordingly. Okay, so when we click on that setup, now remember we've only selected our y values. Okay, we want to enter in our x values as well. Okay, so let's go ahead and click on Add x-axis and click on this data range thingy. Okay, and we want to select a range. So we're going to type in, we want column C, so C2 colon C7, okay, because that's the range of our values. It's the table is kind of covering it up a little bit, but we'd be going from this cell over here, which is column C, row 2, and we go all the way down to row 7 here. Okay, so if I click OK, it'll plug those values in for me. Okay, and so you can see now our graph looks like this. Here, I'll even move this down a little bit so that it makes it a little bit easier to see. Okay, there we go. All right, let's change the title here, because right now it just says P, because that was the column of the thing we highlighted. So let's click on Customize and Chart and Axis Titles. I'm just going to do P versus V as our title. That should be enough. Okay. All right, and there's our graph of pressure versus volume with our data points entered in. Okay, you can see we have this nice little decay curve going on. But notice that we don't have these dots connected. We just have disconnected data points. So we want to draw a curve connecting them. Now, you could select the graph that joins each of these points, but the problem is you won't get a smooth curve that way, okay, unless you have like absolutely perfect data. Okay, and with experimental data, you very rarely do. Okay, no matter how good it is, there's going to be some deviation there. So what we want instead is a curve of best fit, which is called a trend line over here. So to do a trend line, go back to that series option. Okay, so you can click on that. By the way, if this is ever closed and you're trying to figure out how to get back to this, if you just right-click anywhere on your graph, you can pull up this menu accordingly. If I click any of these data points, actually, and right-click on them, well, I guess actually you get the same menu. But in any case, we want to change this series here. We want to add a trend line for that. So if I click on that, again, this pops up. All right, so we have this menu, and we're going to go down here to where it says trend line. We're going to check that option. Now, the default for a trend line, or a line of best fit, is a linear one. And you can see that that's not very appropriate for what we've drawn. Okay, it's cutting through our data points, but it's definitely not matching them. So instead of a linear one, you go to this drop-down menu, and we're going to select power series. Okay, so we're going to get a power series, and you can see that matches a lot better. Now, while this just puts the line in there, we want some extra information. So I'm going to have the label show us the equation. So I click on that label drop-down menu and click Use Equation. And I'm going to check this box that says Show R squared. All right. The R squared value is your standard deviation. Standard deviation is a statistical device that helps us see how well do our data points, our actual data points, line up with our line of best fit. It essentially measures the distance between our data points and the line of best fit. Okay, and it's going to be a number lower than 1. The closer you are to 1, the better your data is. And so you can see here that we have an R squared value of 0.999. That's amazing as far as experimental data goes. So pat on the back to me. I got us some really good data when doing this experiment. You can see again, it's not perfect. If you look at the points, you can see they're not perfectly centered on the line. You can see this point over here is a little bit above it. This one's a little bit below it. That's going to happen. And that's fine. You're not going to get perfect data, but this R squared value tells us that this is pretty good. I think anything above 0.9 is generally, pretty good data. Okay, so yeah. So anyway, that's why I want you to include your R squared value when you submit your graph to me, just to show me that you're thinking about, about that fit of data. It's also a quick way to show me if you've kind of messed up somewhere on your drawing your graph, since I know what your data is going to be. Anyway, so yeah, so this is basically our graph. Here, I'll close this so you can see that a little bit better. But yeah, so here we have our graph of pressure versus volume. Okay, and that is what our that's how we want to graph that first graph. Okay, so again, you can draw this manually if you like, and maybe your instructor might want you to do that just so you can get some practice at manually drawing graphs. But you can see here, this is what your graph should look like when it's drawn by a computer, when it's drawn mathematically perfectly. Okay, so you notice there's also, of course, a second graph, so you should draw that. So let's get to work on that one. So we again want to plot pressure for that. So let's insert a new chart for that. Okay, and we want a different x-axis here. Here we're going to use that D column for 1 over volume. Okay, so feel free to add D2 colon D7. Okay, hit enter, or I think I guess if I click that, whoops, I guess I should have entered that there. My bad. D2 to D7. Now hit enter. There we go. Okay, so notice that we've got our x values here are going to be, that range of 1 over volume. Okay. Now, again, we want to get a trend line here. So let's go to customize. And it probably helps to label this so we don't get the two graphs mixed up. So this is pressure versus 1 over volume, the inverse of volume, just so we remember that. And we want our, oops, sorry, not the legend. We want the series. And go to where it says trend line, select that. For this graph, of course, we have a linear trend line. This is going to be a straight line. So you can leave this at the default of linear. That's going to be a good thing. And of course, don't forget to include the equation and the R squared value. Again, notice the really nice R squared value that tells us that this is a good line of best fit for our data. Okay? All right. The reason I want you to have the equation on here as well, you can use your graph to predict stuff. So we can, if we have a pressure or an inverse of volume, we can, kind of figure out one from the other using this line, using our graph. But if you want to do it mathematically, using the equation, you can do that as well. All right, so you can just plug in values for x or y and solve them, one for the other. Just remember, your y values are your pressure, your x values are your inverse of volume. Okay, so that's up to you on how you want to use your graph accordingly. I'm pointing this out because in Part B of Charles's law, the lab has you use your graph to find out certain values, and it also asks you to sort of extrapolate it backwards and figure out what the what the volume is at a particular temperature. You can do that graphically. It's kind of hard to extrapolate on this. You can do it on Excel pretty easily. I haven't really quite figured out how to do it on Google Sheets. But that being said, once you have the formula of your line, you can plug those numbers in and solve. You can plug in one number and solve for the other. Okay. So if you have something on your x-axis, so if you want to find out where this intersects your x-axis, well, your y value would be 0 at that point, and you just solve for x. Of course, that's for another graph, so I'm getting ahead of myself here. But my point is that you want to include your equation when you're plotting your trend line, because it's going to be useful for things like that. Okay, so here we have our two graphs, and that's essentially, I think, all we had to do for the graphing part of this. So I'm going to scroll down and just like lower this. So I have my two graphs. I could probably lower this a little bit more. So just click and drag that down a little bit. So there we go. So it's snapped together like that. All right. So there's my data table over here on the top. Here's my my pressure versus volume graph and my pressure versus inverse of volume graph. Now, when you're uploading this to Blackboard for me to grade, the best way to do this is to export this as a PDF file and then upload that file. So click on File, click on Download, and select PDF document. Okay, so click on that. And you can see here we've got a preview of this. Notice that here the default here is landscape mode. And you can see this is getting cut off. So I'm going to click on Portrait. There we go. And that looks a lot better. So actually, it looks like we're able to fit everything on one sheet. So good job. If it doesn't, if something gets cut off, feel free to play around with this. You can change the scale. You can go back to cancel this, go back to the original spreadsheet and move things around so that they fit better. But then or you can if it's hard to get everything to fit on one page. Even with playing that stuff around, feel free to move this second graph to another page and, and have this be more than one sheet. That's okay. I have that be more than one page. So I think there are probably ways to do that by playing around with this. So I'm not going to get into that. All right, and then you just click and export and allow you to download this as a PDF file, which you can then upload to Blackboard. All right, so let's see. Here we go. Okay, so once you get to the end of the graph of pressure versus one of the volume, you can see we have some follow-up questions on this section of the lab on Boyle's Law. Now, to be honest with you, questions 4, 5, and 6 are just sort of general questions, and you've probably noticed as a rule, I like you guys to do questions that have to do with the lab, and the other questions are kind of optional. Again, check with if you're not one of my students, check with your individual instructor over how they want you to do these post-lab questions. But if you're one of my students, you definitely have to at least do questions 1, 2, and 3 for this section of the lab. Okay, because this is tied into your actual data and its analysis of it. So So go ahead and make sure you do these 3 questions at least from this section. Okay. Now that brings us to part B of this lab, and that's on Charles's Law. Now here, this doesn't have an experimental section. Here they've provided the data for you, but you are still going to manipulate it the same way. You're going to analyze it the same way we did with our previous experimental section on Boyle's Law. So you can see here we have different volumes and different temperatures corresponding to those volumes. Please note that all of these temperatures are in degrees Celsius, and if you recall, for gas laws we have to use absolute temperature. We have to use Kelvin. So be sure to convert each of these numbers into Kelvin. Again, you can do that manually, or you could do this in your spreadsheet program. Okay, so just as a reminder, to get from degrees Celsius to Kelvin, you add 273 degrees. Okay, 273 Kelvin. So your numbers here should all be positive numbers. Okay, because even though you have negative temperatures here, when you add 273 to them, you should get a positive answer, because obviously you shouldn't get anything below 0 Kelvin, because that's absolute zero. Okay. Likewise, you could manually go in and calculate the volume divided by a temperature in Kelvin. So this L over K here is just to show you the units. It's just to let you know we're taking our volume in liters and we're dividing by our Kelvin temperature, not our degree Celsius temperature. Okay, so take this column divided by this column and write these answers here. You should notice a kind of a pattern in those numbers. So don't freak out if that you know, if the number all winds up being the same. That's actually kind of normal. That kind of shows Charles's law. Anyway, yeah, so you're going to go ahead and graph that as well. So here is a second graph. So if you want to graph this manually, feel free to. If you want to graph this on a spreadsheet program, like whether it's Google Sheets or Excel, like I just showed you for part A, you're welcome to do that too. I'll leave this one up to you. So if you're one of my students, you have to do part A using Google Sheets or Excel, all right? But if you want to do part B, you can do it either way. You can draw this graph either manually, on a sheet of paper and then send me a picture of it, or you could plot this in, you can go ahead and copy this table into Google Sheets or Excel and get Google Sheets to do these calculations for you, and then use it to plot the graph accordingly. Okay. For the questions you've got to do for part B, again, the last couple of questions, so the questions 5 and 6 are just general calculations. They're not tied into specifically to your lab, so I'll make those optional. And again, check with your instructor on how they want you to do this. But you have to do questions 1 to 4. 1 through 4, you have to answer those for this lab, okay? So notice that questions 2, they all have to do with your graph, essentially. Question 1 kind of has you look at that general trend between volume and temperature. You generally look at, for question 2, they're asking you to sort of extrapolate backwards and figure out what is your, the temperature or what is your volume or your temperature going to be when your volume is 0. That's what they mean by predicted Kelvin temperature of absolute 0. They mean that when you look back at your graph and your graph is going this way, they want you to extend the graph all the way back and see at what temperature does it cross that x-axis. Now, if you're using Google Sheets, like I said, it's kind of hard to extrapolate that way. I'm not sure exactly how to extrapolate a graph on Sheets. I could show you on Excel if you're interested. But once again, if you have the equation of the graph, you can figure that out just by plugging those numbers into the formula. Since your formula is going to be y is equal to mx plus c, where m is the slope of your graph, you just set a y value of 0, right? Because that's where where it's crossing the x-axis, and then solve for x. All right. Anywho, yeah. So the other stuff, again, you're just reading your graph basically. You can either plug these numbers into your equation, or what's probably a lot easier is you are going to you can just like look at your graph and say, all right, my volume of 4 liters, what's my temperature? So you just kind of just go across to your graph and then go down to see what the temperature is. Okay. All right, so that's it for this lab. If you have any questions, let me know. Yeah, good luck. Let's try and keep that steady. See if I can feel out the balancing here. Oops. Try and minimize how much. Stay there. Oh no!